Okay, welcome back, everybody. If you recall from last time, we talked a lot about how to count, and in particular, we started talking about the size. How would you talk about the size of a set? What does it mean for two sets to have the same size? And we agreed that two sets have the same size if they can be what? If they Good. If they can be put into one-to-one correspondence, right? And so, in fact, when we count, this is all we're doing. We're actually putting the numbers from 1 through 8 into one-to-one correspondence with the people in the first row. 1, 2, 3, 4, 5, 6, 7, 8, right? There are many ways that could be done, right? I could have also done 1, 2, 3, 4, 5, 6, 7, 8. That's another one-to-one correspondence, okay? But all we need is one or some one-to-one correspondence in order for me to say that the numbers 1 through 8 has the same size as the set of people in the first row. With me? Okay, so once we had that notion, we said, okay, that's what it means to count. So we could talk about the size of a set. I could say there are 8 people in the first row because I've just put this set into one-to-one correspondence with the first 8 numbers, and this set into correspondence with the first 4 numbers, right? Okay. So then we began to ask, well, what about infinite sets? What about sets that have more than a finite number of things in them, in some sense? So the natural numbers were an example. We proved that the natural numbers, in fact, were infinite, which wasn't necessarily obvious, right? Because there might secretly have been a one-to-one correspondence with the natural numbers and maybe the first 8 numbers, perhaps, right? But we showed that if there were one for the first 8, there would have been one for the first 7. And if there were one for the first 7, there would have been one for the first 6, etc. And then basically that would bring us back to the base case of an induction, right? The set of all natural numbers is not in one-to-one correspondence with the set of one element, right? That's what we did last time. Okay, good. So we decided to call any set that has the same cardinality, the same size as a set of natural numbers. We decided to call such sets what? Countable. And we showed, in fact, last time that the rationals are, in fact, countable. Very good. So what I want to do today is I want to say a little bit more about countability and uncountable sets, uncountability. We need to define that. And I want to show you a proof that, in fact, a set and its power set must have different cardinalities. Okay, so we want to do that. And then in the second half of the course, we want to start of the lecture, we want to start talking about metric spaces. Okay? Okay, so that's the plan. So let me just remind us that so here's the plan. We want to talk about countable sets. So I'll just say what the plan is. So more about cardinalities. And then later on, we'll talk about metric spaces. So let's begin with a theorem. Last time we showed that set of all rational numbers is countable. There's something that proof, if you recall how that proof went, we said, oh, well, we could certainly write down all the countable numbers, all the rationals, as fractions in some kind of array. You remember that? And the array went this way and this way, right? And we said, okay, it's countable if the rationals can be listed in some order as a sequence. And, of course, the problem is with the array that we had, which looked something like this, etc., we need to find a way to wind our way through this array and hit every fraction, right? Now, what would be wrong with just going down the first row in my list? So x1, x2, x3, x4, x5, dot, 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 dot. Never get to the second row. Okay, so that would all that would show is that the first row is countable. So what did we do instead with our argument? Of course, this is all, I'm doing this as a shadow, and so if you're watching this on video, you're not seeing anything. But how did we wind our way through this picture? We said, oh, here is a, okay, I'll do this for the benefit of people who can't see anything. So we had an array of numbers, and we said, let's do what with this array? Let's wind our way through. We can certainly hit everything this way, right? Everybody agree? Etc. Okay. Okay. So that was the argument. This was the picture of the proof that the rationals are countable. But I claim it's in fact a picture for another proof. I mean, we just did something very general. So here's the theorem we want to prove. The theorem we'll prove is that the countable union of countable sets is in fact countable. This is one of the most important facts about one of the best ways to show that a set is countable is to write it as the union of a countable union of a bunch of countable sets. Why is this picture really the same picture for this proof? Well, let's just imagine that, so here's a proof. Let's imagine the sets that we are going to take the union of as sets A1. Okay? So let's say that each of the A1, A2, A3 are countable sets. So would you agree, the way I've written this, that this is the countable collection of sets? Why? I've indexed them by numbers, integers, whole numbers, natural numbers. 1, 2, 3, ... right? Okay? And what I'm saying is that each one of these is a set that is itself countable. Okay? So if it's countable, it means it can be listed in a sequence. Good. So consider, we'll write out the diagram like this. A1 is a set of, how about little a 1, 1. Then maybe the next thing in the sequence I'll call little a1, 2, little a1, 3, little a1, 4, little a1, 5, ... With me? Just one of you is with me. Okay, great. And then a2, let me give it some names too. What would you like to call it? Not little a21, it's little a21, little a22, little a23, etc. Okay? ... Now, an a3 similarly. Little a31, little a32, little a33. Okay, excellent. Here we go. Keep going. I'll let you do that. Now, can you suggest a way for me to show that everything in the union of these sets is going to be countable? Well, you could do it how? By this kind of, I would be careful about calling this a diagonal argument, because that name we reserve for something else. But let's zigzag. This is usually called the zigzag argument. Let's zigzag our way through this array, right? So the zigzag here again starts with this one. That's the first element. That's the second. That's the third, fourth, fifth, sixth, seventh, etc. And you see it's exactly like the argument we had for the fractions. Okay? Everybody happy with that? Happy with that? Well, I'm not so happy with this. Well, okay, so your objection, which is a reasonable objection, is what if one of the sets is in fact not countable but finite, right? Okay, and I didn't address that in this theorem. It's actually, this theorem's only talking about countable unions, countable sets, but that is something I want to come back to, okay? But another objection might be that, maybe a particular number or a particular object here lives in many sets. So I would have a listing, but it would list maybe some things many times, which is not what I want. So what can I do? Yes, Bonnie. Okay, and what did we do with the rationals? Okay, that's good. That's one way to think about it. If something is in the set already, you skip over it. Another way to think about it is you could just show that this is true for any array, and then remember the theorem that says the countable subset of a countable set must be countable. Then you'd be done, right? So if you just look at all the things here, some of them are repeated more than once, but if you take a subset where everything's only chosen once, it's still countable. Are you with me? So this is enough to show that this set can be listed. So the union of A sub I, where I goes from 1 to, and this is the way you normally write a countable union. This is also countable, which I've abbreviated countable. Okay, this is countable. This countable union, countable sets is countable. Now, I want to point out that whenever you're talking about an arbitrary union that is not necessarily countable, we use a different notation, okay? So notation, we'll use the union of, okay, suppose you have a bunch of things. Now, if the index, if the thing that you're, if the collection is uncountable, you can't use whole numbers as an index, because that would make the reader think that you're talking about what? A countable collection. So if you want to refer to something that's not necessarily countable, the traditional way to do that is to give the subscript, usually alpha or a Greek letter, and then you union over all alpha in some index set. So here, J is an index set. So what did it use? Use this for possibly uncountable collection. Oh, I didn't define that word yet. Okay, possibly, well, okay, I'll define it in just a second. Possibly uncountable collection. Okay, here J is an index set. That's the set of all things that you're going to sum over in some sense. Take the index from, okay? Okay, let's see. What else did I want to mention? There was a question here about, well, what about if one of these sets is finite? Well, what could you do? You could imagine if, let's say, some of these sets are finite, well, then this thing just terminates, right? But if it terminates, you can think of it as like an empty block. And what you're looking again at is a subset consisting of the non-empty blocks of an array that is countable, right? So in fact, this theorem is also true if you replace all the words countable here by at most countable, where at most countable includes being finite. Okay, so you want to take the finite union of countable sets, that's still countable, or finite, right? Or the finite union of finite sets is finite, right? Okay, so that is also true as well. Okay, let's see. What's another thing I want to point out? Oh, this is amazing. This theorem is amazing. That's the other thing I want to point out. Why is it amazing? Why is it amazing? Just take a look at this. Let's see. Example. The set of, let's see, computer programs that you could possibly write. Let's see, the set of computer programs. That's, you give me a computer program. What is a program? How do you normally code up a program? You code it up using some language, right? Which consists of letters or symbols, right? Yes? Oh, and what do you do with those symbols? You string them together, right? Okay. So a program you could think of as a collection of symbols, right? Each program is a collection of symbols. How many symbols? Well, a particular program has how many symbols in it? Finitely many symbols, and each of those symbols can have how many possibilities? Finitely many, if it's an alphabet of some kind, right? So each program is finite. What about the collection of all computer programs? Okay, it's the union of all 0-character programs, 1-character programs, 2-character programs. How many 2-character programs are there? Only finitely many, right? Right? Yeah, finitely many. That's right, because if there's the alphabet has 26 letters, for instance, then it'd be 26 squared such programs, right? Or what? Not all of those will be real programs, so it's a subset. Are you with me? So, in fact, what we have here is a set of computer programs is finite. Would you agree? Not finite. Countable. At most countable, anyways. But it won't be finite because you actually have infinitely many. I mean, each of the lengths is a particular. There are countably many unions, and they're not empty. So, what you know is this is countable. Why is that an amazing fact? Well, it's something you might observe. But check this out. What did we show last time? What did we show about the size of R? It's infinite. It's not countable. So R is not countable. And so now I'll define this word, which you already guessed. We say it's uncountable. And so the definition of uncountable means it's not finite, it's infinite, and not countable. Just what you would expect. Okay. R is uncountable, yet the set of computer programs is countable. So you know what this means? It means that there are some real numbers that can never be the output of a computer program. Right? So let's call a real number computable if, through some algorithm, you can compute its decimal expansion up to a specified number of places. Right? You input the number k, and the program outputs the kth places of the real number. That's one of these computer programs. Right? So what that means is there are some real numbers that are not computable. There are some real numbers that cannot be the output of a computer program. So, amazing fact. You can just deduce just by this argument. There are real numbers that are not computable. So this is the term here, not computable. So what that means, a computable number is one where the input is a number of decimal places and the output is all the decimal expansion up to k places. Means they can't be specified to arbitrary precision. What? Really? That's an insight we get from mathematics that would not be possible almost just by thinking about this directly, right? About computer programs, right? Interesting. Really interesting. On your homework, you're asked to show that the set of algebraic numbers is countable, right? Algebraic numbers means what? Those are anything that could appear as the root of a polynomial integer coefficients, right? And you use a very similar method, right? You think about, okay, well, let's see, what kind of polynomials could I have? Well, those are specified by the coefficients. How long could the polynomial be? Well, it could be, many, 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 many terms, but finitely many terms. Okay, and the homework problem suggests a way to count them that it will allow you to write as the countable union countable sets. Okay. Computable numbers are actually bigger, larger than the algebraic numbers. I mean, we have, we can think of computer programs that can spit out third roots and fourth roots and fifth roots, right? Computable numbers, for instance, pi and e are computable. We know how to do that, right? But what we're saying is there's lots of numbers. In fact, way more numbers are not computable than are computable, right? But it's only the computable ones we, in some sense, work with, right? Or we know how to work with. Amazing. How many people think that's amazing? I think it's kind of amazing, right? It's amazing. Okay, excellent. Great. So how did we show that R was uncountable? Well, we used an argument due to Cantor called a diagonalization argument. And what I want to show you today is, in fact, that is an example of something even more general. So the general fact is a theorem about power sets. So let me remind you what a power set is. So given some set A, the set of all subsets will be called the power set. It's denoted by a symbol, 2 to the A, and there's a reason for that. It is the set of all subsets of A. Okay, I feel like this is slipping here. It's the set of all subsets of A. Okay, so example. Here's my set. Maybe my set is, let's see, cyclops, smiley, square, triangle. There, that's a set. Okay. What's a subset? Well, would you agree that, for instance, this set, D, which consists of cyclops, smiley, and a triangle, is a subset? Would you agree that E, which consists of just triangle, is a subset? Would you agree that empty set, the set with no elements, is a subset? Yes? Oh, okay. These are elements of the power set. R are elements. These are sets that are themselves elements of 2 to the A. How many elements are in 2 to the A in the power set? 2 to the 3? Is that a coincidence? Which has, in fact, 2 cubed elements. Do you want to see why it's not a coincidence? Check this out. Would you agree that D corresponds to a particular binary number? Namely, tell me which ones are in. Check, check, not. E corresponds to, oh no, this is wrong. Check, not, check. Yes? This is not, check. Yes? What's empty set correspond to? Not. Right? Do you see? And now you see there are, in fact, that 2 to the cubed elements. Okay, so that's why we have this notation. It just makes us think of subsets. Subsets are just specified by 1s and 0s, aren't they? Yes? This is the fundamental idea then in proving our most amazing theorem. So this is Cantor's theorem. Georg Cantor. This is this diagonal argument this is what's called his diagonalization argument, or diagonal argument. It actually dates to 1891, but his proof that the real numbers were uncountable actually didn't at first use a diagonal argument. Okay, so that preceded it. That was like 1870 something, maybe 1874. But Cantor's diagonal argument holds for things much more general. So what it says is, if you have, for any set A is not, cannot be put in one-to-one correspondence with its power set. This is actually a good time to tell you about some mathematical etiquette. If you read the handout on good writing that I passed out, I mentioned that when you're doing formal mathematical writing, it's usually not a good idea to start a phrase or a sentence with a symbol, because it can be confusing, right? If you start a sentence with the letter big A, it looks like you're about to, A is an article, right? It's also true of phrases. So one way to fix that here is, because it can be confusing with the comma, A, is just to put a few words here. We have. Okay, so if we were doing formal writing, you'd want to not start a phrase with a letter. Although this is informal writing on the board, so I won't hold myself to it in class. Okay, let's prove this. Proof. How are we going to prove that a power set is not, cannot be put in a one-to-one correspondence with a set? How should we start this proof? The claim is that there does not exist a one-to-one correspondence. So what's the easiest way to start this proof? Suppose there is one. Then we have something specific to work with, don't we? And we'll try to get a contradiction. Good. So suppose, proof by contradiction, suppose there exists, again shorthand, a bijection F that goes from A to 2 to the A. Okay, so this is a bijection. I might even emphasize to the reader. Now, what does this mean? This function will take what? Something in A, like a smiley face. And it will output what? A subset, like D or E, or empty set, for instance, right? So notice that what this means is every little a gets mapped to f of little a, which is a subset of A. Right? So an example might be, it might be something like this. It might be smiley gets mapped to, I don't know, smiley triangle. Right? Could be something like that. Are you with me? Okay, good. Now, we have such a bijection. What should we do? Write it out in some sense, right? Now, okay. Now, if you recall, so I already claimed that this is somehow related to the proof that R is uncountable that we did yesterday or last time, right? How is it related? Suppose there were a bijection. Then, Willie? Okay, you could try to, okay, you said the word list, and I'm a little uneasy about the word. Okay, so one reason I'm worried about the word list, I like your idea. I'm just going to avoid using the word list because we don't know that A is necessarily countable. This is going to be true for any set A, in fact. A might be hugely uncountable. But whatever it does, it's going to mimic, in the countable case, what happened with our proof that real numbers are uncountable. So here's the idea. I'm just going to show you the idea here. And maybe, for instance, I take an element in A, and I'm associating to that element f of A, which is in the power set. Yes? And, so I'm going to construct, I don't know, whatever. It's a function, right? I'll draw up a table here. So maybe, for instance, smiley corresponds to some set. Okay? And again, I also want to avoid writing this as a sequence because that would make it imply that I'm talking about something countable, which I don't mean to, right? So Adam would rather have me just write all the things that are in the subset in a jumble, right? So maybe, I don't know, maybe it contains this and this and this and maybe this and star, right? There's a whole bunch of things in here. With me? You could, if it was countable, you could list it, okay? But it's not necessarily countable. Subset. There's a bunch of other things maybe. It might not even be finite, right? It could be also uncountable. It could be really crazy. Okay, now here's another element. And again, I'm going to try to avoid making this look like a list, but that's almost unavoidable. Here we go. Maybe there's another element like double smiley, which maybe has elements like this. Triangle, star, Cyclops smiley, star of Bethlehem, boat. Okay, lots of things, okay? And maybe star corresponds to some other things. Star, boat, puppy dog, stuff. Okay, other stuff. Okay, I've just written a few out. Okay, and I didn't write them in a list, even though it looks like it. Okay, happy? Okay, now what are we going to do here? What is going to be the analog of the diagonal argument that we used for real numbers when we wrote out to every integer a real number on a list that had a certain number of decimal places? What did we do? Good. In that example, when we wrote out the decimals, we said let's show that there's a real number that's not on the right-hand side by making it different from every decimal expansion in the nth place. Yes? Okay, what's going to play that role here? I want to show that there can't be such a bijection by showing that there is a subset that can't be on the right-hand side here, anywhere in this correspondence. Yes? And I'm going to do so by making it differ from every possible thing on the right-hand side. Yes? How am I going to make it different? In what place? Jenny, a suggestion. If you know the full idea, maybe just give a hint so people could come along with us. Good. F of A is a subset of A. A subset of big A. Ooh, interesting. Okay, so Jenny said everything in, here's the full set. Would you agree every subset you can talk about the subset, specify a subset by deciding whether some element is either in or not. Is smiley in this set? Yes. Is square in this set? No. Is triangle in this set? Yes. Right? Okay, so I want to construct a new set which differs from everything in this list. Yes? In the what place? If on the right-hand side I associated, for instance, in this picture, suppose I associated smiley and square and triangle with this particular subset. In the smiley place. Yes, I'm going to construct a set that differs from the smiley element of the list in the smiley place, right? Or in this case, in the squared place, or in the triangle's place. So if I were to do this for this particular picture, I'm really interested in constructing a set that is what? Instead of 1, 0, 0, it's 0, 1, 1. And I claim, if that's the case, this is a new set, square and triangle, can't be on my list anywhere because it's different from all these things. Are you with me? Good. That's the basic idea. Now we just got to make that precise here. So what is the smiley place here? Well, is the smiley place is, I want to know, is smiley in the set? Is it? Yes. What's the, well, that's Cyclops place, right? What about smiley, regular smiley? No, yeah, and let me just go ahead and say this, with all the things in here, let's say this has no smiley in it. That's sad, no smiley. Oh, it's got a Cyclops smiley, though. Okay, sorry, tangent. Good, this doesn't have smiley. Good, what's the star place here? The star's there, so is this star in it? Yes, good. So what's the new subset I would construct? My new subset, should it have smiley in it? Cyclops smiley? No. Should it have regular smiley? Yes. Should it have star? No. Good. In general, what's that set going to be? This is how you motivate this construction. So we're going to let B be this set that I claim is not in the image of F. So before I write let B, let me just say what we want is a subset B that's not in the image of F. Can't be the image of any particular element. Yes? And now we have an idea that Jenny suggests looking at. What is it? Well, let B be the set of all things that have what property? Let's call it little a, such that little a is what? What's going to be true about little a? Yeah, I'm going to find all the regular smileys that don't live in their image, their own image, right? So I'll let little a, such that little a is not in F of A. Oh. Hey, that's nice. That's beautiful. Okay, now of course, this is a proposed thing. Let's see if we now believe that this is actually not in the image of anything. Period. Let B equal blah, period. Okay, great. So what's the argument? The argument is, what if it, let's suppose it was in the image. This is now just a matter of writing down the intuition. We'll just compare. So if B were equal to f of x for some x in A, why would this give a contradiction? It's a big if here, right? This is the if that's trying to show this is by contradiction, right? If B were in the image, what would go wrong? What should I look at? What if this set were on the right-hand side? What set should I compare it to? X's set, right? Whatever x is. So if B were f of x for some x in A, so in this picture, the claim is this set B is somehow corresponding to, here's the idea, this set B corresponds through F to some x. Oh, well, what would we then look at? If B were f of x, then consider what's true about x. Consider x and consider x. Is x in B? No, why not? Yeah, if if x were in B, then x would not be in f of x. But x not in f of x would be contradict the fact that x is in B, right? So is x in B? No, because if it were, because then x would not be in f of x, but f of little x is B. So x in B implies x is not in B. Contradiction. Yes? Okay, so if x is in, we've just shown x can't be in B. But if x is not in B, then what does that mean? But then, that means x is not in f of x, which equals B. But this is a definition of B. So then what? X is in B. Again, contradiction. Either way, we get a contradiction. So what's the only alternative now? If either way we get a contradiction, that must be false, the fact that B is in the image of F. So B is not in the image of F in F equal f of x for any x in A. That's the end. Such a bijection could not have existed. That's the desired contradiction. Okay? Drew, are you happy with that? Pretty nifty, right? Very, very good. Very good. This was Cantor's beautiful diagonal argument, most general form. I just want you to know that this concept that now we have many different sizes of infinity met with a lot of resistance in the late 1800s. Okay, one mathematician called it a plague that we would never rid ourselves of. I mean, it was and ultimately it contributed. I don't know if some of you heard this story. Contributed to Cantor going crazy. Okay, it was hard for him to take the rejection of his peers, many of whom did not welcome these ideas when they were first presented. So let's give an example of how you might think about this power set. What's an example of a power set of R? So what we learn is there are many different sizes of infinity. There are many cardinalities, right? So, for instance, what is a set with cardinality 2 to the R that has the same cardinality as the power set of the real numbers? Well, I claim you know one already. Another way to talk about subsets of a set, if this set is a set of real numbers, is to associate to every real number a what? A 0 or a 1, right? What is that? That's just a function from the real numbers into the set 0, 1. So notice that 2 to the, if you like, 2 to the A has the same cardinality as the set of all functions from A to the set 0, 1. So all functions. This is just by membership, by the membership relation. So if you want, 2 to the R has the same cardinality as the set of all functions from R to 0, 1. There's a set that's automatically huger than R. Okay? I mean, what does that look like? You know what functions like that look like, don't you? Here's a graph, 0, 1. These are basically functions that can be sometimes 0 and sometimes 1 for all real numbers. If I want to graph such a function. Don't make me keep going, please. Yes? It might be one some of the time, for a whole interval. Okay. Interesting. Yes, Willie. Yes, yes. In fact, this is so the question Willie asks is, does this mean there are infinitely many infinite cardinalities? And the answer is yes. So consequence of this theorem is that there are infinitely many. In fact, it is true, uncountably many, but it actually doesn't even make sense to say how many there are, but there are infinitely many cardinalities. And they go something like this, right? The cardinal numbers go something like this: 0, 1, 2, 3, 4, ... Then at some point you have the first size that's not finite, and that's called LF null. And then, of course, you can argue that there is a first size or cardinality that is not LF null, and that's called LF1. And so on. There's one that's bigger than that. That's LF2, etc. But beyond that, you can go for a while, but it actually turns out that these cardinalities are indexed by the ordinal numbers. And I'm going to spend a fun lecture later on in the semester talking about ordinal numbers. But there are tons. And the continuum hypothesis, which I referred to last time, is basically the following fact. This cardinality is the cardinality of Z, of the integers, yes? And the cardinality of the reals is often called the continuum, the cardinality of the continuum. But what you might ask is which one of these is the cardinality of the continuum? So the cardinality of R is sometimes denoted by a little c. That's the continuum. But you might ask yourself, where does it belong in this picture? And the continuum hypothesis says that, the claim is, the hypothesis suggests that the cardinality is actually LF1. That's the question. And what's known is that whether the answer to this is yes or no is actually not provable within the axioms that we have. So it's actually could be true, taken to be true or false, and not change the other axioms of set theory. So the continuum hypothesis, you can read more about this if you want, which says that LF1 is the same as C, is what's called undecidable. It's provably undecidable, meaning independent of the axioms of set theory. Zermelo ZFC axioms is what they're known as. Kind of surprising fact that a statement about the real numbers you would expect to either be true or false. But in fact, this is undecidable, and there are models in which it's true and models in which it's false. Amazing. Other questions? Yes, Emil. Uh-huh. Would that have a different cardinality? No, I don't believe so. I think you could construct easily a bijection if you want. Yeah. Here's another question you might ask. You could ask, oh, what if I demand the functions to be continuous? Is that your question? True? You were thinking about that. Let me just suggest that you continue to think about that, because it is actually a question you can answer by the time we're done with this course. Okay? We haven't talked about what it means for a function to be continuous. But how many people think the answer to that question is yes? Do you think that if I make this continuous functions, that the cardinality would still be bigger than the real numbers? How many people think yes, bigger? How many people think it's the same as the real numbers? Most of you are not raising your hand. You're like, oh, I don't know. I haven't thought about it. Yeah, okay, I would encourage you to think about, I'll let you guys think about that. Okay. Yes, Willie.
So if you take that, the continuous hypothesis to be false, in other words, it's not equal to L1,
Yeah.
does this suggest another cardinality, or is it then just unknown?
Well, it suggests that there is a set that has cardinality in between that of the reals and the natural numbers. Yeah. And what a strange set that would be, right? The thing is that if you could produce such a set, then that would answer the question, wouldn't it? So don't expect a construction anytime soon, at least with the current set axioms that we have. Yeah. Yeah, very interesting questions. Okay, excellent. So this idea is going to pop up quite a bit, countability, uncountability, as we're doing other things. But now I want to switch topics and start talking about metric spaces. So one of the things that's very beautiful about all the stuff we're doing, in addition to allowing us to talk about things like real numbers and functions on real numbers, it's way more general than that. We have tools now that will let us work with lots of collections of things that we're going to develop tools that allow us to work with collections of things that aren't just real numbers. This is why it's important to talk about metric spaces. So what is a metric space? Well, as the name suggests, a space is like a space, right? It's more than just a set, right? You could have a set of things, but when you start talking about spaces of things, that kind of implies that there's a notion of what? Space, big, small. There's some way to move throughout the space. Yes? Right? Okay. And so this is the idea when we use the word space, that it isn't actually a set that's endowed with something extra. And often it's a metric. Okay? So the idea of a metric is a notion of distance. So here's a question. How to measure distance? Okay. Now, if you're talking about the real line, well, there's a standard way to do that, right? You could talk about the distance between 2 points. But you could be talking about other things. You could be talking about spaces of a space that might be three-dimensional space, right? You could be talking about spaces of phylogenetic sequences, right? You give me a bunch of the genetic code of a human and a rat and a rabbit, and I might want to know which of those genetic codes are closer in some sense, right? With me? Okay. So how are we going to measure, what do we mean by distance, first of all? Okay, so how do you measure distance? You might in, let's say, the R to the N, or in the set of genome sequences, just to have you think of a biological example where this comes up. Okay, well, so here we're going to define a notion of distance, and this will be called a metric. So a set X is a metric space if it has a notion of distance. That's basically what we're going to say. If the following is true. There exists a metric, we'll call it little d. What's a metric? It's a function that takes in pairs of points and spits out what? A number, a real number, in fact, a positive, a non-negative real number. So here we go. It's a function from x cross x. This is the product. It means it takes in two things, and it spits out a real number. Okay? Such that the following is true. Okay, there are three properties that have to be true about this metric. If you such that for any 2 points, for all p and q in X, three things hold. The first thing is you want the distance between p and q, d of pq. That's a real number. You want it to be what? Well, if it's going to be a good notion of distance, let's demand that it's always non-negative. How's that? Is that reasonable? Talk about distance, right? Okay, and one other thing. We want it to only be equal to 0 only when, if and only if, shorthand, p is q. That is, distance between two things that aren't identical is not 0. Okay, that's the first property. The second property, what do you think is I'd like to be true about this distance between p and q and its relationship between the distance between q and p? Should be the same. You have a name for that property you might want to call it? Symmetry, yes. We call this the symmetric property. Okay. The first one naturally is called what? Non-negativity. Right, okay. I'm not going to write that down. Okay, the third thing is something that we've already seen is true for the Euclidean distance, the usual notion of distance, or for the absolute values, and that is the distance between p and q better be less than, here's a picture, p, q, r. What's the relationship between these three distances? Distance PR to the plus distance of RQ. You want this distance to be less than or equal to for all R in X, for any intermediate point. And this has a name, not surprisingly, it's called the triangle inequality. One of the most important properties of a metric. Okay, are you with me? Okay. That seems like, a very natural notion of a distance. Let's see some examples of distances here. What are some examples of a distance? Well, the first one, of course, is just the notion of absolute value of the difference of two numbers, right? That's definitely a distance. So here's the space R. It's a metric space with what distance? How about the distance between x and y to be the absolute value of x minus y? Yes?
Is it possible for a metric space to have multiple metrics which satisfy those properties?
Yes. In fact, we're going to see some examples here. So if we were to be more, if there's any confusion, we actually specify what the metric is. Yeah. So here, I would write, for instance, if there's any confusion, I would write the metric is a pair. It's R together with D. Okay. Yeah. Okay. Let's see. How about Rn? Here's the usual. These are the usual notions. Rn with this distance between x and y. Well, it's just going to be the square root of the sum of the squares, x1 minus y1 squared plus xn minus yn squared. Everybody's seen this metric before, yes? Distance? It's the distance formula. These are both these, and would you agree that this just gives this if you have just one coordinate? The square root of a square of a number is always positive or non-negative, yes? So this is known as the Euclidean metric on R. Now, I want to point out that anytime you have on Rn, anytime you have Rn and you don't, the metric is not specified, this is the one that you assume it is unless otherwise specified. This is sometimes called the usual. So this is the usual metric. It's the one that's understood if it's not specified. If not specified. Okay, any problem You assume it's that one unless someone tells you otherwise. But there are many others. I mean, here's another one. What if I were in R2? So maybe I have the following distance. So I'm going to call this distance. Maybe I'll give it a special name. I'm going to put make a little staircase. And I'm going to define the distance between 2 points to be, distance between 2 points to be, what's called the staircase metric. How about instead of taking the square root of the sum of the squares, let's just add up all the absolute values in every coordinate. There's only 2 of them here, but I guess you could do Rn. This is true for Rn. You could make this Rn. I goes from 1 to n. Now, in R2, what would this look like? Well, if I want to measure the distance between 2 and 3, 4, I would add up this length and this length, right? So that is a staircase. That's why it's called the staircase metric. Notice that using the staircase metric, this is sort of another way I could measure that length. It's the sum of all these lengths. Okay? So the staircase metric gives a different notion of distance than the Euclidean notion. Okay? So I'll call this staircase metric. Oh, interesting. I mean, there are tons of others. These are just a few. Let's talk about some other spaces that are slightly different than Rn. What if I were, let's see, here's an example. Actually came up in a paper that I wrote for a biology journal. So you might look at a phylogenetic tree, or just any tree in general. What is a tree? It's a bunch of nodes connected by edges, and there are no loops. There's no cycles. Okay. So take a tree. Now imagine this not as a graph, which is basically, you think of this as a discrete object, but as a continuous object where you can live anywhere along an edge. And I ask you now to measure the distance between x and y. How would you measure the distance? How would you do that? Oh, that's one way to do it. You could count the number of vertices between. Something like that. Yeah, it would be fine, actually, with the following two, the last two. But the first, it might be 0 if they were on the same edge. So that would not be quite a metric. It'd be what would be called a pseudometric. Okay, which you don't need to know about. But pseudometrics satisfy B and C, but not A. If it were a continuous space, you could just add up these lengths. That would certainly do it, right? That's a notion of distance. So this is the tree metric. Distance from x to y is the length of the shortest of the path between. It's well defined on a tree. There's a unique path, shortest path between, right? There's actually just one path between. Okay. Okay, great. Now, I'll let you think about why this satisfies a triangle inequality, but it does. Here's another example. Suppose my space X is a set of genome sequences. And for the moment, I'm just going to ignore the possibility that some sequences have different lengths than others. Imagine you have a bunch of sequences of the same length. So for instance, I don't know, how about one sequence might be the sequence of nucleotides. There are how many nucleotides? 4. Okay, yeah, G, C, T, and A. So suppose I have, I don't know, some sequence like this. G, A, T, T, A, C, A. How about something like that? I just made that up. Okay. What if you had another sequence that, was something else, like A, G, A, T, CAT. Okay, so what's a good notion of distance between x and y? How would I measure the distance between x and y? For the genome sequence, I'll call it DG. What's a good notion? Give me a suggestion. Maybe the first one that would come to your mind. Good, that's one way to do it. Number of differences. Number of letters that are different. Is that a metric? We'd have to check these three properties. Is it only 0 when they're equal? Yes, good sign. Is it symmetric? Yes, excellent. Satisfy the triangle inequality. Does it? How many people say it does? How many people say it doesn't? Okay, yeah, it's worth thinking about, but in fact it does. It does satisfy triangle equality. I encourage you to try to prove that. Okay, great. How about the following? Here's another example. This actually comes up in mathematics and physics quite a bit, even some in economics. And that is, often you're dealing with a space of functions. I won't say exactly what space right now. I'm being a little purposely vague. But you often have functions that you're dealing with, right? So for instance, in calculus, you might be dealing with function. Here's one function. And here's another function. Okay? Tell me how you'd measure the distance between these two functions, right? How would you measure the distance between two functions, right? In economics, a function might be a pricing scheme, right? You price commodities with prices, right? That's a function, right? Okay. How would you define distance? I'll give you a minute here to think about this. Give me a notion of distance between two functions. Distance between f and g. Any ideas? There are several different ways, actually, but I would just love to hear some ideas. Harris?
Integrating across the absolute value of the difference.
Ooh, interesting. Okay, so you're suggesting this distance. Of course, we don't know what integral means yet, but let's assume later on we will. You might say, let's look at the absolute value of the difference integrated from a to b, as long as this was defined between some a and b, yes? So notice that to be very careful here, for this distance to be defined between any pair, it better be defined on continuous, well, it doesn't have to be continuous integral, but just to be very nice, keep it very nice, you could define it on continuous functions on an interval AB. Right, that's the space. A space of continuous functions on AB. We often write the space C of AB, where what curly C means continuous functions, a space of continuous functions. Okay, that's definitely one way of doing it. A little worried about some of these things, but they're still true. It's going to be 0. Is it true it's going to be 0 exactly when f and g are equal? Yes, if it's continuous. But if it's not continuous, then we'll talk about what that means later, but you'd have to be a little more careful then. You'd have to place functions in equivalence classes. Yes, Dylan had another idea. I'll call this di for integral. What did you say now? D what? What do you mean by max? What do you mean by the greatest value? What do you mean by the largest absolute value? So you want to look at f of x minus g of x, yes? And you want this, there's a bunch of these to compare, aren't there, right? So here maybe the maximum, not maximum, the largest, well not largest, the Supremum, thank you. Because this maximum might not be achieved, but the supremum will be because it's a collection of real numbers. If we have to now define the space we're on. So first, the supremum over all x in whatever the interval is. In this case, actually, we don't need to restrict it to a particular interval, do we? So it could be defined over all r as long as we're on the space of continuous bounded functions. And so this has a special name. We write C, and we have a subscript b. And this could be defined on all of r. As long as it's bounded functions, then this supremum then the distance will be bounded, and the supremum exists, right? The situation you might run into is this situation. Imagine these two functions where the supremum, these distances just get larger and larger and larger, but the maximum doesn't exist. But the supremum will. That's why we use the supremum. This is actually called the supremum distance. So I'll call this d sup. It's the sup, sometimes we say sup norm. Okay, and it's a very, very natural one to consider. Excellent. Okay, great. Let me finish then with a couple of ideas that we will build and develop next time. So, in a metric space, one of the most important concepts, which helps you get a sense of what the metric is doing, is the concept of an open ball. What's an open ball? Well, you think of a ball as round object, right? And mathematically, that would be the set of all points whose distance is less than or equal to some number, yes? Or less than some number. That'd be open, right? So an open ball, we often write n sub r of x. This is the neighborhood. That's the way the book talks about it. Of radius r is basically going to be the set of all y such that the distance from x to y is less than r. Okay. Now, if you want the closed ball, it's the same definition except what? Less than or equal to, and you might notate it with a bar over the top. Okay. And so if you want, just to show you here, for the regular notion of distance, Euclidean metric, the balls look like you expect. They're like this, right? That's a ball. But here, the balls look very different. I claim in the staircase metric, the set of all points whose staircase metric from here is the same actually looks like something else. It looks like a diamond. That's an open ball in the staircase metric, right? It's a diamond, right? It's a diamond centered around here. I'll let you think about that. Okay. Okay, so why are balls going to be important? Well, balls are going to be important because we can use them to define the notion of what it means for things to be close, as in limit point. Okay, so let's say if you want to talk about a limit point, what does it mean for a point to be a limit point of this set? If you have some set, a limit point. So let me just make a definition. Let me make a picture here. Here's a picture. What does it mean for this point to be a limit point? Well, what that means is you give me any ball around this point, and no matter which ball I take, I will always have points of what? Of this set in it, in the ball. That's what it means to be a limit point. This creature is not a limit point because there is a ball that doesn't even touch E. So we're going to say P in P in X is a limit point of E, which is a subset of X, if every neighborhood, that's what a ball is, an open ball is a neighborhood, of P contains a point of E. A point Q that's not P, and such that Q is an E. It's important that there be some other point that is not, that is in the set, in the neighborhood. Okay. That's what it means to be a limit point. And so, for instance, if I have here's a picture here. Suppose I take the set of reciprocals, 1 at 1, 1/2, 1/3, 1/4. Does this have a limit point? I claim 0 is a limit point because any open ball around this set, would you agree, contains a point, yes? Of this green set? Any open ball contains, it should be open. We usually dot those. Contains a point of the green set. So the yellow point is a limit point of the green set. Okay? We're going to explore the concept of limit point in great detail next time. Okay? I encourage you to get a start on the homework for this week. You can do most of the problems already. And I want you to come see the tutors or me during office hours if you have questions. All right, see you next time.